Okay, here we go. Today's Friday, April 27th, and today we talked about a variety of things. Everything has to do today with acids and bases because that's our new topic. So we talked about properties of acids and bases. We talked about what the difference is between a strong and a weak acid or base. It turns out the difference between strong and weak is the same no matter whether it's acid or base. We talked about neutralization reactions. And we defined what acids and bases are through two different definitions, the Arrhenius definition and the Brønsted-Lowry definition. Important stuff to do tonight or over the weekend here. I need you to read and outline chapter 16.1. I also need you to memorize these strong acids and bases. As far as we're going to be concerned, anything that's not strong, any of the strong ones that I have you memorize, we're going to consider that they're weak acids or bases, and they get treated differently as we're doing different types of problems. Okay, so let's go straight through this. The unit is about acids and bases, and these are the things that we're going to be working on. I might as well read through them. All right, so we're going to define and understand similarities and differences between properties of acids and bases. So we've got definitions and similarities and differences in their properties. That we're doing today. Okay. Understand the difference between the Arrhenius and the Brønsted-Lowry definition of acids and bases. We will do that today. Conjugate pairs we won't talk about until Monday. So that most of that we're getting done today. Identifying the difference between strong and weak acids and bases and understanding the difference is something we're going to talk about today. So we're getting rid of 3 of these check marks today. Remember, we just did equilibrium where we were doing K expressions. It turns out that we can do a Ka, we can do an equilibrium of an acid or an equilibrium of a base, and we can construct Ka and Kb expressions and actually solve for them. So we'll be doing that next week. We also want to understand what neutralization reactions are, which we're going to do part way today, and we're going to do part way next week. This last bullet is actually something that we're probably not going to have time for this year. So we're not going to do it just because we're getting up on the end of the quarter here, and we just won't have time. If we get the time, we'll do some of that. All right, here we go. Properties of acids. This is pretty simple stuff. You just have to memorize it, okay? Acids taste sour. We already know lots of acids. Citrus has acids in them, so lemons and limes and oranges and grapefruits all have a bit of a sour taste to them. It's because there's acid in them. Colas have sour taste too because, same reason, there's acid in them. Sour Patch Kids, sour gummies, same thing. You've got acids on the outside of those, crystalline acids coated on the outside to make them taste sour. Acids are corrosive to active metals is what your book is going to tell you. The difference between an active metal and any other metal, let's talk about what a non-active metal is. Non-active metals are metals such as gold, platinum, silver, that are very hard to get to react. Active metals are ones that are easily reactive. Okay, so acids won't necessarily be corrosive to gold and silver, although they could be if they're the right kinds of acids. All right, we've got 2 kinds of litmus paper. We've got blue litmus papers, we've got red litmus paper. All litmus paper is the same, basically. Here's what it is. It's a piece of paper that has a chemical on it. The chemical is there as an indicator to tell you what kind of substance you have when you dip the piece of paper in it. You dip the piece of paper in it, it gets wet, and it either stays blue, if it's blue litmus paper, or it turns red. If it's red litmus paper, it either stays red or it turns blue. Either color that it turns to, it's telling you the same thing. If it turns red, it's acid. Okay, so red means acid. There are actually more papers out there called pH papers that actually give you a rainbow. It gives you a spectrum of colors all the way from red to blue. Red still means acid there, blue still means base there. It's just that you now can tell how acidic or how basic depending on which shade of the color spectrum you're at. Okay, all acids conduct electricity. What this means is that they disassociate to produce ions in water when they actually get put in water. Okay, here you can see hydrochloric acid being put into water. It's disassociated into this is the hydronium ion, and this is an important ion to know. I would write this in the notes. and put a star next to it. The hydronium ion is actually the ion that is responsible for being caustic in an acid. This is partially what defines an acid. So like I was saying, that's the hydronium ion. That is actually what is caustic, what's going to cause chemical burns if you were to touch it. It's not the actual hydrochloric acid, it's this hydronium ion that's extremely reactive. Notice here, guys, it does produce ions. We've got ions produced on the right-hand side of the equation. And also, another thing that's important here is that, before I go on to that, let me just point out this. This may look complicated, but it's really not very complicated. Every single acid starts with hydrogen, okay? What that is going to do is it's going to lose the hydrogen to water. One extra hydrogen means you've got 3 hydrogens, which is hydronium. The stuff that's left over, well, let's see what's left over. The chlorine ion here is all by itself. Okay, so that's basically what an acid does when you pour it into water. It produces hydronium ion and leaves its anion, its chloride ion in this case, all by itself. All right, now the last thing that I got here is that acids react with bases in a reaction called a neutralization reaction, which is on the next slide. Neutralization reactions always are the same. They always contain an acid and a base, and they always form water and some salt. Not necessarily NaCl, but some ionic compound. If we take a look at a neutralization reaction, this is one right here. Check this out. We got an acid, got a base. They formed water and a salt. There's nothing very difficult here. If you want to try and dissect what's going on, again, we take a look at what's going to happen here. The hydrogen is going to break off the acid. Where does it go to? Well, let's take a look. The only place with hydrogen over here is here. There's 2 hydrogens and an oxygen. So what's the hydrogen forming up with? It's right there. Hydrogen and the hydroxide are going to form water together. The chlorine and the sodium ions then are what's left, and they're going to form the sodium chloride on the right-hand side. Now, if you can remember all the way back to October and November, we were talking about complete and net ionic equations. We can write a complete ionic equation for this. Everything's aqueous. Well, 3 of the things are aqueous, so we can write the disassociation of them and show how that looks. Now, check this out. The hydrogen ion turns into water, so we can't actually cross that out, but the chlorine ion and the chlorine ion are exactly the same, so we can actually cross both of them out. The sodium ion and the sodium ion, hey, they're the same too, so we can cross them out. The hydroxide ion did change, it's now water, so what we wind up with for a net ionic equation? It formed water. Exactly what we thought it was going to do. All right, strong versus weak acids. There is nothing I can do to help you here with tricks or gimmicks. We need to memorize these. These 6 acids. This is hydrochloric, hydrobromic, hydroiodidic, nitric, sulfuric, and then hypochloric acid. You need to memorize those. There's nothing else beyond that. If I ask you if an acid is strong, if it's one of those 6, you're going to say, yes, it's strong. If it's not one of those 6, you're going to say it's weak because you don't recognize it. Don't bother memorizing this list. That's the short list. Okay. There is one small trick that I can give you with these 3 acids, the hydroacids. It turns out that the 3 hydroacids happen to be right next to each other on the periodic table. Okay. Those 3 are formed with hydrogen, all form a strong acid. Nothing else is going to help you there, though. All right. Strong versus weak acids. So why is it that we need to differentiate between strong and weak acids? Well, equilibrium was last chapter. Notice here this is not an equilibrium reaction. This is a completion reaction. Okay. Strong acids dissociate completely. What that means is that when I take nitric acid and I pour it into water, it's going to completely get rid of the nitric acid. The nitric acid is going to disassociate into hydronium ion and nitrate ion. And the hydronium is going to be formed when the hydrogen attacks the water and becomes hydronium. The nitrate is what's left over here. A weak acid dissociates only partially. What this means is right there. This is a reversible reaction. By definition, it does not ever go to completion, which means basically here, the perchloric acid that's here, when I dump it into water, only a small amount of the perchloric acid is going to take its hydrogen and attack the water to become hydronium. That means that there's still a fairly large amount of perchloric acid left. Okay, so I've only got a small amount of hydronium that's ready. So the difference between these is I've got a lot of hydronium ions made, and here I have only a few hydronium ions made. The difference between this is if I put my hand into this beaker, I've got all those hydronium ions. The hydronium ions are what's responsible for actually doing the chemical reaction that's corrosive, so my hand is going to get messed up pretty quick. Down here, with a weak acid, there's fewer hydronium ions. My hand's not going to get messed up quite as quickly, but here's the interesting thing. This is an equilibrium shift. If I put my hand into this reaction, that means some of these are going to get used up, corroding my hand. That means the reaction is going to shift right to make more. They're going to get used up, and the reaction is going to shift right again. They're going to get used up. Reaction is going to shift right again. It's going to take a while, but my hand can get just as messed up by putting it in this as that. It's just a matter of how much time I've got. All right. Another way of looking at this is this. Notice I've got 0.1 molar hydrochloric acid here and 0.1 molar hydrofluoric acid here. The only difference between these two acids, this one is strong, hydrochloric, and this one is weak, hydrofluoric. The hydrochloric, take a look. You'll see that there are no hydrogen chlorides left. They have all disassociated, and here's where chemistry gets interesting. Sometimes there are two definitions. I said earlier that hydronium is the thing that makes acids corrosive. Some people prefer another definition that talks about the hydrogen ion. So instead of having hydrochloric, the hydrogen ion disassociates from the hydrochloric, and this is what they say is the corrosive material. Either way, it's a positive ion that has hydrogen in it. So you check this out. We've got, if I counted right the first time, there are 14 hydrogen ions concentrated here that are ready to go, ready to corrode whatever you put in there, be it a piece of metal, your finger, whatever. Over here with the weak acid, I've got 1, 2, 3, 4, 5, 6, 7. I only have 7 hydrogen ions over here that are ready to go. So if I put something in here to be corroded, like a piece of metal or my hand, you're going to find that what's going to happen is these hydrogen ions are going to have to react and be gotten rid of. And then these hydrogen fluorides are going to break apart into more hydrogen so that they can react, and they're going to react eventually as time goes on. That's going to shift the reaction to the right, of course, but it's going to take time. Either way, if you put something in either one of those, they're still going to get corroded. Like I said, this one takes more time. The hydrofluoric takes more time. The hydrochloric is going to happen quicker because it's stronger. Okay. One misconception is people tend to think about pH. We haven't talked about pH yet, but pH is not related to strength. pH is related right here. All right. That is what pH is related to. These two have the same pH, but they do not have the same strength. Skip that. Basic properties. Properties of bases. Bases taste bitter. Dark chocolate is my favorite thing to talk about when we talk about bitter tastes. If you're not a chocolate fanatic, then go to Starbucks and ask for a cup of coffee with nothing in it but coffee. You're going to pay $5, you're going to be pretty bitter about that. But then you have to taste the coffee after that, and you'll find out what bitter actually tastes like. All right. Bases also are slippery. Soap is actually basic. Bases, when you put litmus paper in, bases turn litmus paper blue. It doesn't matter what color litmus paper it is, it's going to turn blue. So you put red litmus paper in, it turns blue. Put blue litmus paper in a base, it stays blue. So you want to use the red litmus paper just so you get a good confirmation. All right. Bases also conduct electricity because they also produce ions in solution. The interesting thing here is acids that we deal with in chemistry class, in regular chemistry, tend to come in liquid form, aqueous forms. Bases tend to come in solid form, so we have to mix them up from the solid crystalline form. All right. Molecular equation here for a neutralization reaction using a base. Check this out. We got a strong, well, we haven't talked about strong bases yet, but this is a strong base. Here's our acid. We got our base. Hey, guess what? Neutralization reactions of bases are going to form water and a salt. Does this sound familiar? There's the hydrogen ion. It attacks the hydroxide ion and becomes water. The leftovers are the lithium and the nitrate, which form lithium nitrate. I don't think there's anything difficult about this. You just have to kind of follow it along. Acids are going to donate hydrogen. Bases are going to accept it. We're going to skip through this real quick because it's a little bit repetitious. Again, water is formed, so is a salt. All right, strong versus weak bases. You have to memorize 12 strong bases because everything else is going to be weak. The easiest way to memorize your strong bases, all hydroxides made with alkali metals are strong bases. All hydroxides made with alkaline earth metals are strong bases. What does that mean? That means lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and francium hydroxide, the alkaline metals, are all strong. Beryllium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide, and radium hydroxide also are all strong bases. Why is it that we care about strong versus weak bases? It's the same reasoning as was with acids. Strong bases dissociate completely. Check this out. Hydroxide ion here, that's what I'm concerned about. That's the caustic bit. So when I put sodium hydroxide into water, I'm going to get sodium and hydroxide ion. The hydroxide ion is going to be completely there. There's going to be no sodium hydroxide left. I'm kind of concerned about that because that one's concentrated. Weak bases, on the other hand, only dissociate partially. So if I'm doing this with ammonia, which is a weak base, into water, now I've got ammonium ions and hydroxide ions, but I've only got a few hydroxide ions. Okay, so I've got lots here, and I've only got a few down there. So that's what's going on there. Okay, we're almost to the end here. We have to talk about definitions. The nice part about the definitions here is if you understood what I've spoken about previously, is these definitions are going to fall into place and it's going to make some sense. All right, Svante Arrhenius is a Swedish scientist. He's known as the founder of physical chemistry, and he did most of his work in 1890, about 1890. He defined what an acid is. He was the first person to define an acid. He said an acid is going to be any substance that when we add it to water is going to increase the hydronium ion concentration. That sounds kind of like what we started with at the beginning. I told you that the hydronium ion is what an acid produces. And that's very important. Well, this is why it's important, is because it is part of the definition of what an acid is. All right. A base, according to Arrhenius, is any substance that contains a hydroxide group. Okay, so the substance has to contain a hydroxide group and it has to be able to dissociate to produce a hydroxide ion. What does this mean? It only works for soluble hydroxides, according to Arrhenius. Now, I put a caveat on that. So I said according to Arrhenius. Caveat is this. Arrhenius is working a little bit early in chemistry in the 1890s, and his definition is limited to aqueous solutions. According to his definition here, it has to be in aqueous solution. According to his definition of an acid, it has to be put into water to see if their hydronium ion is formed. So liquids that cannot mix with water cannot be told if they're acid or base. That's a problem. Okay. The other thing is he can't classify substances that sometimes act as acids and sometimes act as bases. Yes, there are substances that go both ways, that can be acidic or basic depending on the situation. And he also doesn't explain why ammonia is a base. Ammonia's chemical formula, if you remember right, is NH3. It has to contain a hydroxide group according to Arrhenius' definition. I don't see a hydroxide group there at all. I see nitrogen and hydrogens. There's no hydroxide, no OH. Okay. Arrhenius' problem was he was born a little bit too early, and he was doing his work a little bit too early. He doesn't have enough information. Brønsted and Lowry, this is an interesting situation in science that occurs quite often. Two scientists working independently at about the same time, coming up with the same explanation. 1923, we got two scientists, one working in Denmark, one working in Britain, Johann Brønsted and Thomas Lowry. They independently proposed the same basic principles for what an acid should be defined as and what a base should be defined as. The benefit that Brønsted and Lowry have that Arrhenius didn't is that the proton has been discovered by this point in time. We know about subatomic particles. What they realize is that acids are really chemicals that are donating protons. What's a proton? Well, what element has a proton in it? Only one proton. Well, that would be hydrogen. All acids, like we said earlier, begin with hydrogen. Hydrochloric, hydrofluoric. All right, they all start with hydrogen. So any species, any chemical that has a hydrogen that it can be donated, usually we write those hydrogens out front, is going to be considered an acid according to Brønsted and Lowry. The nice part about this is that all Brønsted-Lowry acids wind up also encompassing what Arrhenius thought were acids. So we don't change what an acid is by adding this definition. Brønsted and Lowry also had to define what a base was, and what they did was they decided that a base was any species that can accept a proton. So we've got proton donors being acids and proton acceptors being bases. And it turns out that the nice part about this is all Arrhenius bases are Brønsted-Lowry bases. So again, we didn't have to take anything that Arrhenius said was a base and call it something else. They're still bases. Okay. What that means here is this. The hydrogen, when it goes over here to water, means that this is an acid because it's donating the acid, it's donating that proton, that hydrogen. All right. The water here was accepting it when it became hydronium. So it is the base by definition. We can follow this out and we can actually chart out what acids are and what bases are in chemical reactions that way. Okay. Now I've got one worksheet for you to work on. It's called Acid and Base Strength Worksheet. You'll want to read through it. It's a brief summary of what we just talked about. And on the back, you have to decide whether something is an acid or a base and whether it's strong or weak. So you might want to do some memorizing of strong versus weak before doing that worksheet. That's about it. So have a great day.